All right, so we're going to now shift over to Go's most important data structure, which is the slice. Arrays might be the most important data structure as it relates to the hardware, but it's not the most important data structure as it relates to Go. The slice is. And remember, a slice is really a vector. It is that array, but it's dynamic. I always like to say it's like our cake and we get to eat it too, right? We get all the mechanical sympathy of a data structure that's sympathetic with the hardware, but we get a data structure also that's dynamic. So there's lots of things to talk about as it relates to slices. So let's look at some basic mechanics. Then I'm going to get into things like gotchas, things you have to kind of look at, things we'll talk about. And we'll even talk a little bit about strings in Go before we're done. So let's start with the very basics around slices. Now, a slice is part of a class of types that I call the reference types. There's really three classes of types in Go. There's the built-in types, there's the struct types, and there are the reference types. And we just kind of finished talking about arrays, which really are part of the built-in types. Okay, so we're now going to be talking about a set of reference types. And there's slices, there are maps, channels, interfaces, and functions. They all represent this class of reference types. Now, if you look on line 13, you're now going to see the use of the built-in function make. Go has not only keywords, but it also has built-in functions: copy, make, new, cap, length, len. We're going to see these as we move forward. And make is specifically for making slices, maps, and channels. And it's really designed around being able to pre-allocate the backing data structures for these three types. Now, what you see here on this line 13 is we're asking to make a slice of 5 strings. I want you to notice that the slice syntax looks like an array, but there's no value in here. If there's ever a value in here, now we know we're talking about arrays. If not, we're talking about slices. And what that's going to do is construct a slice of 5 strings. Now, what is that going to look like in terms of memory representation? Well, first of all, understand that a slice is always a 3-word data structure. So we're going to get back in our fruits variable this 3-word or 24-byte data structure. And the first word, remember words can either be pointers or ints, it's going to be a pointer. And it's going to be a pointer to that backing array of those 5 strings. So here we are, our 5 strings, 0, 1, 2, 3, 4. And yep, that backing array is going to be set to its 0 value. So that pointer is a pointer to the backing array, which drives this data structure. Remember, it's an array, but it's a dynamic array. The next word represents the length. And in this case, it will be 5. We're asking for, on the call, a length of 5 strings. And then we have a third value, which is capacity. And when the length is set to 5 only, then the capacity will follow. Now, the length is very much like the array. It describes the total number of elements from that pointer position that we can read and or write to. And we can read to all 5. Capacity represents the total number of elements that exist in the backing array, not necessarily what you can read and write. In other words, you could have more capacity than you have length. And we're going to get there at some point. Now, notice that, and this is what confused me early on about Go, is that we have this kind of array syntax. I mean, I'm inefficiently doing this. We could use that literal construction to do this, but I'm just showing you that this slice has that array syntax, even though at the end of the day, this is the data structure in question. Now, you cannot go beyond the bounds of the length. So if I try to run this code here, this code is going to error out at runtime. All of a sudden, we're trying to go beyond the length, index 5, not going to work. And one other thing I want to show you here on line 25 is that we're using our value semantics to move this slice value across the program boundary. When we get over to calling print, print is going to end up with its own 24-byte or 3-word data structure. So just like our built-in types, we're going to be using value semantics for our reference types to move this data around our program. If you think about it, I'm trying to take some cognitive load off your back. Out of the three classes of types we have in Go, built-in, reference, and struct, or user-defined, The reference types and the built-in types use value semantics to move that data around. So once again, I don't want to see a pointer of that slice, a pointer of a channel, a pointer of an interface. I don't want to see these things. There are some exceptions that we'll get to, okay? But I don't. But you got to be really careful about the reference types, because even though we're going to use value semantics to move them around our program, when you're reading and writing with a reference type, you're using pointer semantics. And this becomes really important. There's a duality to the reference types. You know, when we're working with the built-in types, we're using our value semantics to move them around. You're also using your value semantics to read and write. You're operating on your own copy. But in this case, every program boundary gets their own copy of the slice value or the channel or the interface or whatever it is. But reading and writing is done through pointer semantics. So it adds a little bit more complexity that we have to kind of remember. But the beautiful part is that all these little slice values, they get to stay on our stacks and we don't pollute our heap. All right. So this is the beginnings here of understanding our slices. Now let me show you another program. And what this program is going to show you here is not only can we set the length during construction, but we can also set the capacity. Look at what I've done on line 13. I've changed this now to add a third parameter, which is 8. And when I do that, what I'm now saying here is I don't want the length to match, or the capacity to match the length. I want a different capacity, which now means that I'm going to be adding 3 more elements, right? 3 more elements, 5, 6, 7, to the backing array. But understand it's length that drives everything. So if we go to print this slice, if we go to read or write this slice, again, we're bound to just the first 5 elements. That's all we can. Length represents the total number of elements that we can read and or write. If we pass a slice to some sort of print function to iterate over it, it's going to be over the length. The capacity represents the total number of elements in this, and capacity really just represents efficiency for future growth that we're going to see. Now, one last thing that I want to show you is the inspect slice function. Now, if we look at this inspect slice function, which we're going to be using later on, I want you to look at the parameter. Notice how this is asking for a slice value. It's not asking for a pointer of a slice. If I saw that in a code review, if I saw that as a field, code review is going to stop. Again, we're going to use these value semantics to move this data across our program boundaries. So everybody can get their own copy of the slice because there's already pointer semantics built inside of it. And what this function does is it iterates over this slice of strings, and it's going to show us how the backing array is a contiguous block of memory on a predictable stride. Look at this. Remember, every string on the playground is 2 words. Every word is 4 bytes. So every string is 8 bytes. And you can see that 080808, there's that predictable stride of contiguous memory that the slice represents. But again, we have that dynamic nature to it. And we may also be saying, well, now we can start talking about the for range. Look at this. I use the value semantic form of the for range here. I'm going to keep iterating this over and over again. Your data semantics have to be consistent throughout your code base. Why am I using the value semantic form of the for range here? Well, we're going to start doing this type of questioning. The question is going to be, what is this collection of? Oh, it's a slice. A slice of what? A string. What is a string? It's a built-in type. What do we use for built-in types? Value semantics. Boom, 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 boom. Now we know what form of the for range we're supposed to be using. We're going to continue to do this type of questioning throughout the rest of this class, and I want you to be able to start doing that. What are we iterating over? A collection of string. What is a string? It's a built-in type, value semantics. Everybody should get their own copy of this string. That's how we're going to be doing it. You know, I can do an entire code review of your entire project without even knowing what it does. Just focus on data semantics, and I'll probably find some bugs out of it. Because when you don't have this data semantic consistency, it's going to produce bugs. All right. So right now what we know is that there's a built-in function named make. It lets us pre-allocate the backing array. We could set just the length, and the length again represents the total number of elements that we can read and write. We can also set capacity, and that defines the total number of elements that are available to us. And as we're going to see, capacity is really for efficiency in future growth.